Okay. So, so we are planning to discuss about current flow in the semiconductor. So in next few classes, we'll discuss about different modes of current flow. So before going to the current flow, um, so let me talk something about phonon, right? So because
Sir,
yes, Bhavesh.
sir, I have doubt that you have give the formula for the density of available state in the, I think, last class.
Yes.
But I saw in the book that there is a power of 3 by 2 in
Yeah, yeah, there should be a
2
power
and
of 3
okay,
by
you have
2. Huh.
right that.
Yeah, yeah, yeah. So, okay, let me, okay, so before go there, let me, I don't know, where is this one? Mhm. I have to check. I didn't remember where is what.
Yes, sir, abhi bhi hai.
There is a 3 by 2 here, right? Huh.
In the back, can you go on previous?
Yeah, so see, there will be a 3 by 2. If I have missed, then you have to include this 3 by 2, right?
Okay, okay.
Yeah. So this equation, we have a 3 by 2. I don't know whether I missed in some of my lecture, but I'm not very sure. Let me see. This is for today. Anyway, so this 3 by 2 will be there.
Yeah, okay.
Yes. Okay. So, okay. So we discussed about electrons and holes, right? So there is another uh, wave or particle will tell. We call it phonon, right? So the phonon, we just have, I'll just discuss little bit about phonon because we'll talk about phonon when we talk about mobility, when we discuss mobility. So phonon, this is um, uh, this is something. I mean, these are nothing but pressure waves in the crystal, right? So the pressure waves in the crystal. So uh, see, in quantum mechanics, the electron holes are also waves, right? So this they behave like waves and they propagate, because that's why we define this wave function, right? Similarly, phonon has also a wave function. So these are pressure waves in the crystal. So the origin of phonon is, let's say you means we discussed about atom, right? So in atom means sorry, we discussed about crystal, and in a crystal the atoms are arranged in a periodic manner. So uh, so with means at room temperature, at a given temperature, uh, so these atoms also vibrate. They are not fixed in the crystal lattice, right? So they are vibrating, and they are so as you increase the temperature, the vibration will be more, right? So when I talk about vibrating, basically they are moving, right? So basically they are so they have their substitutional sides at the crystal lattice side, right? So along the lattice side, these crystals are also vibrating, right? So that means all the atoms are vibrating, right? So this vibration, right? So this vibration is I mean, vibration will depend on temperature, and and this vibration will create a wave, right, in the crystal, right? So these are called pressure waves, because pressure waves, and these waves we call it phonon, right? So right, and the energy of the phonon is terms h bar omega. So omega is the frequency of oscillation, right? So basically, if an atom is vibrating about its mean position, when all the atoms are vibrating about its mean position, so it will have some energy depending on the how, I mean, what is the frequency of vibration, right? And this energy we call it E equal to h bar omega in quantum mechanics term, right? So uh, since these pressure waves are created in a periodic crystal, right? We also have a band structure of phonon, right? So like we have band structure for electrons and holes. So we also have a band structure for phonon, right? So means we'll not go in detail to the phonon band structure. If you do some advanced courses um, uh, in solid state physics, or if some of you will do condensed matter uh, physics, so you'll also discuss about phonon band structure, right? So so based on the phonon band structure, basically phonon band structures are also same, right? So you have a Brillouin zone, and in between Brillouin zone, so you have phonons, and phonons have different bands, right? So so depending on the energy of the phonons, so we divide the phonons into two kind of, mostly we discuss about acoustic phonons and optical phonons, right? So these acoustic phonons, basically their frequency is low, so it's like a sound wave, right? So very low frequency. So if the vibration is happening at very low frequency, so uh, so we'll call it acoustic phonons, because acoustic phonons has very low energy, right? Optical phonons have very high energy, right? So when you discuss about the band structure of a phonon, so band structure of phonon means we have energy as a function of momentum, right? So in the energy in the y-axis, you have acoustic phonons with very low frequency. Then we have optical phonons, right? So so you imagine, um, so when the electrons are moving in the crystal, right? So electrons are moving at the same time. We have also phonon, right? So um, basically you have pressure waves, right? At absolute zero temperature, definitely the atoms are stand still at their lattice site, right? But with temperature more than absolute zero temperature, they will start vibrating, right? As you go on increasing the temperature, the vibration will be higher, right? So the vibration means your frequency of oscillation around lattice sites will be higher, right? So you could imagine, um, in a single plane where the electron is moving, all the atoms are vibrating, right? And they are creating some wave, and also we have a EK diagram, right? We call it phonon band structure, right? At the same time, different planes also atoms are vibrating, right? So so this will give you different kind of phonons, right? So basically uh, so that's why phonon band structure is very important. But why I'm telling this, because so when the electrons are moving, right, uh, so we have another because the crystals is vibrating, we have also some pressure waves, so the electrons cannot move freely, right? So we will discuss about electron phonon scattering, because electron and phonon will interact also, right? So so that's the reason I just introduced you to the phonon. So just keep in mind the phonon uh, are pressure waves in the crystal, and the energy of phonon is h bar omega, and these phonons are because of vibration of atoms around its lattice site, right? Okay, so with that means we'll talk about the current flow in the semiconductor, right? So current flow, the current flows because of two mechanisms. One is uh, drift and diffusion. You might have already uh, I mean discussed this drift and diffusion, drift current, diffusion current. So drift is nothing but the electron holes move with the aid of with the help of electric field, right? So if you take a semiconductor and apply electric field or apply voltage across the semiconductor, so the electron holes, the electrons and holes in that semiconductor will move, right? So that is the drift movement, right? So that means they are moved with the help of electric field, right? Another one is diffusion. So if you take a piece of semiconductor and there is a concentration gradient in two parts of the semiconductor, right? So the electrons, so let's say we have a semiconductor, and in one side I have very high concentration of electron, and other side I have low concentration of electron. So since there is a concentration gradient, so the electrons will move from high concentration side to the low concentration side, and this movement we call diffusion, right? and the current is nothing but movement of electrons and holes, right? So this move, that's the current in semiconductor devices will because of both drift and diffusion, right? So we'll start with drift. We will start our discussion with the drift. So if I say I have a piece of semiconductor here, right, and I apply a voltage across it, right? So let's say I applied a voltage across it, right? So you know that the inner, so basically if this is a semiconductor, so if I plot the voltage from right side to left side, let's say this is my x direction. So if I plot v, vx, how does v varies with x? So you'll see that here you're 0, then at this point you have v, right? And your voltage is linearly varying, right? So this is a typical right. So assuming that it's a semiconductor with a particular conductivity, so your voltage uh, will linearly vary, and this point is 0. So here voltage is 0 and here it is v, right. Okay. So if there is some electron here, let's say I have electron here, so it will experience no voltage. But if I have electron here, this will experience some voltage, and if I have electron here, this will experience some voltage, right? So the electric field, right? So we know if I write the electric field, sorry, not electric field. So let me write because see, we discussed that we discussed the potential energy and kinetic energy of electron, right? So when I'm not applying any, basically what we're telling that the electrons are mostly at the bottom of the conduction band, right? So now if you give some potential, right, that means your energy band diagram will also move up and down, right? So so this energy, when I'm talking about energy is nothing but in this case the charge. So basically, if you think from electron point of view, so charge is negative, so energy is minus q times b. So if E equal to minus q times b, if I do d by dx, it is nothing but q times dv by dx, and this is nothing but minus dv by dx. So minus dv by this is your electric field, right? So here you see uh, this relationship. So so d by dx, this d by dx is nothing but how your energy changing with so basically your potential energy, right? So it's changing with x. So if electric field is 0, that means d by dx is 0, right? If electric field is positive, that means d by dx is positive, right? If I'm plotting, if the electric field is from left to right, let's say electric field is from left to right. So if you plot E as a function of x, the E will have a positive slope, right? If your electric field is from right to left, right, then E will have a negative slope, right? Because so right. So now if I plot the energy band diagram, right? So energy band diagram, what I'm doing in energy band diagram, right? I am just plotting the potential energy of electron as a function of x and the potential energy of holes as a function of x, right? This is the energy band diagram, right? So so now what I'm telling, if I have a semiconductor and I have applied a voltage V here, uh, right? So you have electric field in this direction, right? So your energy band diagram will look like this, right? So your energy band diagram EC. So EC is the bottom of the conduction band, right? And EC is nothing but the potential energy of electron, right? Similarly, EV is the top of the valence band, right? And EV is nothing but the potential energy of holes, right? So this is how they change with applied voltage, right? So this is the energy band diagram with the application of positive, I mean V here, right? So you could see this part. This part is nothing but minus QV. So when I'm not applying any voltage, my energy band diagram will look like this, right? Energy band diagram will look like this, right? But because of application of voltage, so there is a slope, because the moment I apply voltage, there will be electric field, and if there is electric field, there will be d by dx, right? And your energy band will bend, right? So there will be a slope, right? Okay. So I have electric field in this direction, right? So I have electric field in this direction here, right? So because of the electric field, right? So your electron and hole have a particular charge, right? So then it will experience a force, right? So the electron holes will start moving, right? So this force, if I talk about this force, this force equal to how do I write the force? So so electrons have some charge, let's say Q, right? Minus Q, and if they experience a field E, so what will be the
Minus
what will be the force?
QE.
Yeah, force will be
minus
my charge into electric field minus QE, right? Okay, so so this is the force, right? But we are not we are interested um, to find current, right? So basically we are interested to find current, right? So so basically how to define current? So current is nothing but, because current will be there if there is a movement of charge, right? So if the charge here, the electrons move from one place to other place, then we'll get a current, right? So current is nothing but if charge into velocity, right? So charge into velocity, and since this is drift, then I'll write drift velocity, right? Okay, so okay, so let's say I have a semiconductor here, right? I apply a voltage. So how do I do? So basically, on say voltage, if I want to find the current, then I'll because electrons will flow. So I have electric field in this direction. So electrons being negative charge, they will flow in the opposite direction of electric field. That means they will flow from left to right. So if I have a particle count, or if I count the number of electrons, so how many number of electrons I'm collecting at this point per second, that is my current, right? And this is nothing but it will depend on the velocity, how fast the electrons move from the left hand side to right hand side, right? So the current is charge into velocity. So, and the velocity, this Vd, is because of electric field, right? So you see, if you go on increasing this electric field, the velocity will increase, velocity of electrons will increase. See, this velocity is nothing but the slope of this line, right? So higher the slope, higher will be the electric field, higher will be the velocity, right? So if you plot this drift velocity as a function of electric field, you'll see your drift velocity will increase, right? And then it will saturate, right? Then it will saturate, right? So this is the typical, right? And I'll not go to the saturation part, because when the energy of the electrons become very high, they actually interact with optical phonons. So moment they interact with optical phonons, their velocity saturates, because of the mobility degradation. We'll talk about it later, right? So let's not talk about this saturation part. So this, if you look at this part here, right? So your velocity is linearly dependent on electric field, right? So as you go on increasing the electric field, your drift velocity will increase, and the slope here, this slope here, we call this slope the mobility, because Vd is proportional to electric field, and I could write Vd equal to mobility times electric field. So this mobility is a constant, right? So mobility, so basically when you plot velocity as a function of electric field, so you could also this slope here is mobility. So basically this slope can be different, right, for different conditions, right? even if the slope is same, right? So it could mean, if you do the example of classical mechanics, let's say you have a finite slope and you you have a ball with different mass, right? And if you release that ball will reach the other part with a different velocity, and that velocity depends on the, means how fast, it's basically depend on different conditions, right? Mass of the ball and other things, right? So this constant is depend on the, that's why this constant uh, is depend on the condition of electrons, right? Where they're moving and all those things, right? Right. So this we call mobility, right? So the mobility, uh, right, mobility of electrons, right? Okay. This can be electron or hole, right? So mobility of carriers, right? Okay. So so this but this is valid till a particular region. So your velocity, if you go on increasing the electric field, at some point your velocity saturates, velocity will not increase. And so for for silicon, so this saturation velocity is 10 to the power 7 centimeter per second, right? So the velocity of electrons cannot be higher than 10 to the 7 centimeter per second, and we'll discuss these things later, right? And why this is 10 to the 7. So the saturation velocity is different for different semiconductor material, right? For silicon it is something, silicon, so germanium it will be different, and gallium arsenide it can be different, right? Okay. So now if I want to have expression for current, so let's say I have a semiconductor, let me draw it. Right. So right. So basically, let's take right. So let's say I'm considering a thin sheet here. So okay, so let me give voltage across it, right? So I'm applying V across the semiconductor, right? And uh, if I take a thin sheet, right? So here and another at right, and let's say this distance is dx here, right? So so basically, the moment I apply this voltage, so I have electric field in this direction, right? So electric field, right? So the electrons will move uh, from left hand side to right hand side, and let's say this is my means this is the sheet of electrons I was talking about, right? So so here, so what is the charge of electron? Let me write down q times n number of electron, and area of the sheet is a, right? This is my area of the so this area is a, right? So if I take this area is a, right? Then into drift, so charge into velocity will be my current, right? So this is how right? So then I could write this q n a, and vd is nothing but mu times electric field. This is I here. So right, and E, so basically the electric field, so if the electrons are moving from here to here, so the electric field is nothing but minus dv by dx, right? So dv is the voltage drop between these two, between x and x plus dx point, right? So between x and x plus dx point, so we have a voltage drop of dv. So we could write down this as q mu n a e dv by dx equal to I, right? So then I have q mu n a e times dv equal to I dx. Then if I want to find the total current, so I could integrate it from 0 to L, and I could integrate it from 0 to V, right? Because if I want to find the total current, so basically your voltage, I'm now talking about X and X plus dx, but for a full semiconductor, then the voltage is varying between 0 to V, right? And your X is varying from 0 to L. So if I do that, then this will be Q mu N A. Oh, E concept. No, E will not be there, right? Sorry, mistake. Okay. Uh, Q mu N A V, right? V equal to I times L, right? Your current is nothing but Q mu N V by L times A. So your current density is nothing but Q mu N V by L, right? Yeah, right. Right. So the current is not, so basically if you look at this term V by L, this is nothing but your electric field, and uh, right, and this is your charge, and mobility will give you velocity. This expression nothing but charge into velocity, right? So we know also from the Ohm's law, J equal to sigma times E, right? So Ohm's law also, you know that the current density is your conductivity times electric field. So if you equate both these equations, so you could know the conductivity sigma of is Q mu N, right? So this is my conductivity, right? So basically, your current also depends on a parameter called the conductivity, right? Right, and your rho, if you want to have the resistivity, this is nothing but NQ mu, right? But here we are only considering about electrons, right? So, but in a semiconductor, basically we have both electrons and holes, right? So when electrons are moving in one direction, holes will also move in the other direction, right? So if you have both electrons and holes in the semiconductor, your resistivity, when you talk about resistivity, the resistivity or conductivity, so conductivity we could write as Q n mu n, and also QP mu p, because we'll have also holes, and holes will also move with some mobility. See, mu n will not be equal to mu p, because because holes are moving in the valence band and electrons are moving in the conduction band, right? So holes and electrons are moving in a different bands, so they are moving in different conditions, right? When they're moving in different conditions, their mobility will also be different, right? So your mu n is not equal to mu p, right? And your conductivity, so this is the conductivity of the semiconductor, right? Very standard equation. The conductivity of the semiconductor depends on the number of electrons. So this is, if the charge carriers, number of carriers, so charge carrier is high, then your conductivity will be low, and it also depends on mobility. Okay, so but then here, so you see, if you look from the current here, right? So when you talk about current, the current depends on the mobility, right? Your conductivity depends on mobility. So let's see what is this mobility term, right? So mobility means, in a single sentence, if I want to tell what is mobility, this is, mobility is how easily the electron flow from one side to the other side, one place to other place, how easily the electrons are moving. But this is the ease of flow of electrons or holes, right? This is how you define mobility, right? But what is so difficult for an electron to move from one side to the other side, right? Why it is difficult, right? Why they face some challenges when they're moving from other side, one side to the other side, right? So this is because we have different, we have different scattering phenomena, right? I'll just briefly talk about scattering, um, right? um, when I talk about scattering, so scattering means, um, we could call also interaction, right? um, right, so when the electron is moving, so in a typical, because we are talking about mostly extrinsic semiconductor, right? in the extrinsic semiconductor, we have atoms, right? We have atoms periodically arranged, and also we have replaced some of the, let's say this is silicon, we have also replaced silicon with a dopant, right? So let's say this is arsenic, right? We have a couple of arsenic atoms, right? Because right, so, and these dopants are ionized, right? That means these are ionized ions, right? So basically, uh, because see, arsenic, the atom has already given an electron, right? So these are ionized, right? So when the electron is moving, right, when the electron is moving, so basically what happens, they interact with those ions, right? So they scatter, because your electron has a particular charge and your donor ions has a particular charge, right? In this case, electron has a negative charge and donor ions have a positive charge. When the electron is moving, there is a possibility that there is interaction between electron and these donor ions, right? So there is an attractive force in this case, right? So if the electron is moving with some velocity, if somebody is pulling from the other side, that means the electron is not very free to flow, right? So that is what we call it, ease of movement of electron, right? So this we called ionized impurity scattering, right? And as you go on, right, uh, right, I mean, so if you go on doping more and more, that means we have more number of ionized donors, and the electrons will scatter more, right? Because there are more number of ionized donors, right? So this is ionized impurity scattering. And another thing which is very important in a typical semiconductor is, we just discuss, this is phonon scattering, right? See, what happens is, uh, let's say I have a periodic arrangement of atoms, right? Now let's say the atom is vibrating, right? So when let's say this atom at a particular point uh, is vibrating like that, right? That means the and this atom is vibrating, right? So okay, let me, right. Okay, so here this atom is vibrating around this crystal lattice site, right? So this, every atom is vibrating, right? Right? Every atom is vibrating. But let's say at one point, right, it may happen that this atom, when vibrating at one point of time, this atom is not here, this atom is almost here, right? Because it is oscillating, right? And there is a possibility that this atom is here, but other atom, let's say they have gone to the other part, right? Right, let's say like this, right, right. So what happens, this atom has moved, right, because they are still vibrating along the lattice side, right? So 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 this part, you see here, uh, we had a particular lattice constant, right? So now if you look at these two atoms, the lattice constant has increased from a plus del dA, right? Some delta increase is there, let's say put it a plus delta a, right? Right, similarly, here you see the atomic atoms are come closer to each other, right, while vibrating, right? So let's say this is a minus delta a, right? So this we call dilation, right? This we call dilation, and this part we call compression, right? So see, when I'm talking about pressure waves, right? So basically, if you see these two atoms, the distance has increased, distance has decreased. These two atoms, the distance has increased, right? So and so basically, and they are vibrating continuously, right? And this is generating a wave, right? And this wave we call the phonon, right? And you could imagine, let's say you are selling, means let's say you are selling with a motorboat, right? And somehow you create a vibration in the ocean floor, or you have a wave coming, right? So basically your, means you will be affected, right? Your movement will be affected, right? So similarly, since these pressure waves, uh, when the electron is moving, so these pressure waves will interact with the electron, right? And it will impede, or means it will impede the movement, right? It will reduce the movement, ease of movement of electron, and this is called electron phonon scattering. This is a very common phenomena in semiconductor, because we are not talking about room temperature, right? The atoms are vibrating continuously, and when the electrons is moving in this periodic crystal, that means it is also interacting with the pressure waves from this vibration, right? And you see, you think about it, right? So when you're operating a IC or integrated circuit, right, your chip is becoming hotter, right? So basically, because of current, it dissipates some heat. So with heat dissipation, the moment your semiconductor becomes hot, that means your atoms are vibrating more faster, right? That means it is means the energy of these pressure waves are more, right? Um, so then your interaction will be more frequent, and more means your mobility will be affected more. But you could also think it in a different way, right? So okay, so let's say, you see, I told you, right? So the band gap or band structure is defined by the lattice constant, right? If you different lattice constant, your band structure will be different, right? So here you see, if you look at this, this is the typical atom, right? This is our lattice constant, and but when I move at some point of time, so we have dilation and compression. So if you see these two atoms, they're very close to each other. Two atoms are very close to each other, and two atoms are very far from each other, right? So this you could think of, this changes the band gap. So when you are assuming the conduction band, right? So you have a conduction band, and electrons is moving in this conduction band, and you are assuming it's a flat surface, right? It's a flat surface, but the moment its atoms start vibrating, it will become bumpy, because you see, um, this point, right? If you see this this point here, right? So your atomic the lattice constant has increased momentarily, right? So this will reduce the band gap, right? So what will happen, that your band gap will reduce, right? Here the atoms are compressed, right? Because they have come very close to each other, your band gap will be higher, right? Again, there is a compression, sorry, there is dilation compression, right? So instead of your means, this is a model, right? Don't go by this actually. So now electron is moving in a conduction band, but the conduction band becomes bumpy. This is because of the vibration of this atom. That means the atomic position is changing continuously, right? So when means basically, then the means basically, these are energy walls, right? So when electron encounter these energy walls, there will be reflection, there will be some reflection, right? So this is how it means, these walls, right? This will just impede the movement of electrons, right? And this is called electron phonon scattering, more briefly, right? So this electron phonon scattering is always there. If you go to room temperature, right, absolutely zero temperature, room temperature, there will be electron phonon scattering. If you go to absolute zero temperature, well, there will be no vibration, right? Then means you could get rid of electron phonon scattering. Otherwise, this electron phonon interaction will always be there, and they reduce the mobility, right? Okay, any questions here? I think, I mean, I should take a pause for 1 or 2 minutes at this point. Any question? Sarda, Swati,
No, sir, no questions.
Aditya?
Sir,
Yeah.
sir means how we would estimate that means by scattering mobility will decrease only. It may increase also.
Yeah, I mean, see, yeah, I means basically, I mean, see, the point is, let's say, the means when we're talking about these phonons, right? So basically, means you could imagine, means when I give example, right? Your conduction band was flat, or conduction band is bumpy, right? The moment the conduction band becomes flat to bumpy, your mobility will not increase, right? Mobility will decrease, right? Even when you're talking about impact and ionized impurity scattering, right? So let's say your electron is negatively charged, and we have a lot of donor ions. When they're moving, when the electron is moving in this crystal field, right, is the crystal potential, right? So we have ionized donors sitting there, right? So they could interact. That means electron is moving with some velocity, or let's say it is moving, but there is a positive ions sitting here, and there it will attract the electron, right? So electron, let's say electron is moving from left to right, but there is a force which is attracting that electron movement. So it will, the velocity will little bit reduce, right? So it will not increase, right? So most of the cases when we're talking about scattering, actually the mobility reduces, they don't increase, right?
Okay.
Yeah, but if there is if something, let's say you have means the electron is moving, but you give some force which helps the electron to move faster, that way, in that way the mobility will reduce, right? So mobility will increase, and electron will, means your current will increase. But most of the scattering events, they just reduce the mobility. They don't increase the, means they don't increase the mobility. Right? So okay, so if you go to the next thing here, so let me, so basically, let's say electron, there is two scattering events, because we talked about two scattering means ionized impurity scattering and phonon scattering. So let's say there are two scattering events, right? So this is at the time t 0, and there is another scattering event between t0 plus delta t, right? So right, so the electron is here, the electron is moving, and right, so basically what happens is the electron scatters at this point, but then scattering means the velocity reduces, right? Then between this point there is no scattering, right? So that is the time between two scattering phenomena, and here we call it the means while the electron is not scattered, we call the relaxation, right? Phase where the electron is relaxing, it is not scattered, right? So here you see, between this scattering phenomena, your velocity will increase, because electron will not go through scattering, right? So your velocity may increase from v0 to some point, right? v0 plus delta v, let's say delta v, right? So so this is the velocity they're gaining, right? The electron is gaining. Then moment it again scatters, this velocity will reduce, then it will again, right? So this is how electrons move, right, in a crystal, right? So basically they gain, then they're scattered, they lose energy, lose velocity, then again they gain, then they lose velocity, like that, right? So if I write, right, so if equal to minus QE, because the force, because electrons are moving because of this electrostatic force, Q times E, right? And I could also write down this as m star dV by dt, right? So this is the effective mass of electron, right? And dV by dt, your acceleration, right? So here, Haves.
So due to the scattering, the lattice is also changing continuously, right? It is
Yeah,
vibrating.
yeah, lattice is changing, but these are two scattering events, right? Whatever showed you, these are two scattering events. I'm not talking about lattice here, right?
No, it is vibrating, right?
Yeah, but these are
The
scattering
lattice.
events. Yeah, it may be so, but these are two events, right? So I have one scattering event here. So I have a time there is no scattering. Then I have another scattering event at t0 plus delta t, right? So in this delta t time, I do not have any scattering event, right?
And the direction of that 110 direction is also change, or that plane and the direction of the electron.
No, why the direction will change, right? So if the electron is moving, let's say electron is moving on a plane, right? Right? Let's say that is 100 plane, and it is moving in 110 direction, right?
Yes.
But why this electron will change direction? See, they are moving with some velocity, right? So let's say you think about your car, right? You're moving with some velocity in your car. Suddenly a bump come, right? So basically your car velocity will reduce, right? Or let's say there is a place where you have you have to go up, right? So your car, so these are the all scattering phenomena, right? You could think about your direction will not change, right? Right. So they will still move in the same direction, but if they're moving with some velocity v, velocity may reduce when these they experience some scattering, right? Right.
Initially, they are moving in the 110 direction.
110 direction. I'm telling that they will still move in 110 direction, right?
But the lattice is, if the lattice is continuously changing, is the with respect to the lattice is 110 direction is also changing, or
No. Why the lattice direction will change, right? See, atoms are vibrating its equilibrium position, right? Lattice side atoms are vibrating, right? But this
yes,
direction is still 110, right? Right? So let's say if this is my plane and I have my atoms here, right? And if this is my 110 direction, right? So the atoms are vibrating, right? Right, so they are vibrating in all direction, right? So basically it's a 3D also, right? So right, but why the direction will change? Because this direction will always, crystal direction is 110, right? So let's say the atom at some point, maybe you can have such a configuration, right? Atom is there, but this direction is still 110 direction, right? Right, even if there is a little bit change in lattice site, right? But we have means electrons are still moving in this 110 direction, and the crystal direction is still 110, right?
yes,
Is it clear, Bhavesh?
yes.
Okay. All right. So right. Okay. So now I could write this dV, right? That's QE divided by m star into dt, right? So this is the velocity, right? So basically, if I see dV is means between this 0 point t0 and t0 plus delta t, right? And similarly, this is QE m star. Similarly, dt t0 plus t0 plus delta t. So this is nothing but your drift velocity, because between these two events, whatever voltage gain is your drift velocity. Sorry, whatever velocity you gain is your drift velocity, and this is nothing but QE m star. This is t0 plus delta t minus t0. So this is um, E by m star into delta t, right? So this is delta t is nothing but the time difference between two consecutive scattering events. So, and this is called the relaxation time also, tell q, right? So, and we could write this as minus q tau m star into E, and this here, this part here, right, q tau by m star, right? So this is your mobility, right? This is how your mobility is defined, right? So your mobility, how easily the electrons are flowing from one point to the other point, depends upon the tau, right? So tau is the time difference between two consecutive scattering, right? If there are a lot of scattering, that means tau is lower, right? If tau is lower, your mobility will be lower. If a lot of scattering, then your mobility will be less. And also it depends on the effective mass, right? If the mass is high, right? So your mobility will also be lower. So this depends upon where it is moving, right? So if it is moving in conduction band or valence band, your effective mass will be different. And this effective mass, keep in mind, this is the effective mass conductivity effective mass, right? Not the density of states effective mass that we have used there, right? So this but for your thing, you just keep in mind this is the effective mass. So your drift, well, your mobility. So if I write down, so your mobility is nothing but q tau by m star. So m star is the effective mass. So this effective mass, this for electrons and holes, it will be different because the electron is moving in conduction band, hole is moving in valence band. This tau will tell you how frequently your scattering event is happening, right? If your scattering event is happening more often, then the tau will be very less. That means your mobility will be less, right? and Q is the charge, right? Right, it's the charge of the particle, right? So electron or hole, I'm talking here, right?
Sir, if the scattering increases, the tau will increase, right?
No, tau is the time difference between two scattering event, right? Right. If the scattering is increasing, that means we have lot of scattering events, right? So the time difference between two scattering events is very, I mean, it's low, right? If you have a lot of scattering.
Okay.
Okay, so now if I now plot, because this is now I have to plot the mobility, because mobility is a very important parameter, because your drift velocity or drift current depends on mobility. So if I plot mobility, so mobility as a function of temperature, so this is a very general plot, right? So for a particular, let's say I'm talking about electron, and I have doped this n type. So for a particular ND, so how my mobility change with temperature, right?
Same as tau.
No,
Mobility.
no, I have, I mean, tau is now fixed, right? So basically, if I've taken it, means basically when I, so basic, okay, okay. So here I am talking about two kind of scattering events, right? Right. So I'm talking about ionized impurity scattering and phonon scattering, right? So what will happen to the phonon scattering if I increase temperature?
Will increase, I think.
Yeah, the scattering will increase, because your vibration will be more. The atoms will vibrate more, right, with high frequency, right? So basically your scattering events no, means increase, right? So basically um, you would expect that your mobility will reduce with temperature, right? So which is basically true, right? Your mobility will reduce with temperature, right? But this is mostly the phonon scattering dominant, right? But when you go to very low temperature, right? When you're talking about temperature, or temperature is very low, right? So there the phonon scattering is very low, right? Right. So there, so mostly at low temperature, or even at room temperature, or little bit lower than room temperature, uh, your ionized donor scattering will be more dominant, right? So if I talk about ionized donor scattering, right? So this is phonon scattering. We know that as the temperature increases, your phonon scattering will be more, right? But what will happen to ionized donor scattering? If you increase temperature, what will happen to the ionized donor scattering?
Increase.
Why? Why do you think so? Because do you think your number of ionized donors are increasing with temperature? They're
No.
still there, right? There's still
Yeah.
same number, right? So what will happen? Home?
Sir, I think the number of donor atoms will remain same, but at the same time, with increasing temperature, our
So what
number
will
of
happen to this ionized donor scattering? You are telling that they will remain same, so we'll have a flat line here. No change of scattering, ionized donor scattering with temperature.
uh,
Is it the case? Anybody? Sarda?
Sir, so basically here the ions remain same, but as we increase the temperature, the electrons' energy will increase. So it will overcome the scattering. So
No. Electron
mobility will,
energy. How does the electron energy increase with temperature?
sir, like the kinetic energy of electron,
Hmm.
it will increase with temperature,
Hmm.
that kT by Q.
Hmm.
So as the energy increases, and since the ions are same, but the energy of electron has increased, so it will overcome, like it can overcome that like the pull. So mobility will increase with increase in temperature in this case.
Yeah, so basically you are correct. So your ionized impurity scattering that will increase, means that will reduce with temperature, because see, imagine, uh, so you have a positive ion sitting here and you have an electron, right? And if that electron is moving with, means there are two cases. First case, electron is moving slow movement, or I have a fast moving electron, right? So slow and fast moving electron means I have a higher kinetic energy, right? So basically, as you increase the temperature, right, your kinetic energy of electron increases, right? So if I have two electrons, one electron is moving slowly, or other electron is moving at a very high speed. So in which case your interaction will be higher?
The slower one.
Yeah, in the slower one it will be higher, right? So that's why uh, as you go on increasing temperature, since the electrons are moving fast, so your ionized impurity scattering will reduce, right? So uh, that's the reason you see ionized impurity scattering will have something like this, right? So this is my ionized impurity scattering, right? So you see, so if you add these two, so you'll have something like this, right? You have something like this, right? So this is how for any typical semiconductor, if you take a semiconductor to the lab and measure mobility as a function of temperature, you'll get something like this, right? But the point is, if you go on increasing, let's say this is for a particular ND. Let's say this is for ND1. Now I have I'll take a semiconductor where NDO means it's a different ND. Let's say ND2, and ND2 is higher than ND1. So there your ionized impurity scattering will be even more, right? So you'll see for ND2 it will be like this, right? Because for ND2, where ND2 is greater than ND1, right? So if I have a very low doped semiconductor, there is no impurity scattering. Very low doped means there will be some impurity scattering here, right? So basically, let's say this is ND3, and ND3 is less than ND1, right? So these are the typical. If you see in the papers also, you will see when the measure mobility as temperature with different doping. You see if it is highly doped, uh, your uh, your mobility will be mostly dominant by the ionized impurity scattering, because there are a lot of ionized donors, right? In this case, right? But as you go on reducing the doping, so you will see that this point is moving towards the left, and it is mostly dominated by the phonon scattering, right? For the low doped semiconductors, your mobility will be mostly means mostly influenced by the phonon scattering, right? So yeah, phonon scattering will be more dominant for a low doped semiconductor compared to a highly doped semiconductor, right? So
Sir,
this is the mobility as a function of temperature. This same thing is valid for electrons and holes, right? So even if you do mu n or mu p, you will have the similar plot, right? You have the same plot, exactly same plot. But the
sir,
mobility
when
of holes will be different than electron, because as I told you several times, the effective mass of holes is more than electron, because your holes are moving mostly in the valence band, right? So that's why your mobility will be different. But the mobility as a function of temperature will have the similar shape, right? Bell-shaped curve, right? If you go to high temperature, it will be dominant by the phonon scattering. At the low temperature, it will be dominant by the ionized impurity scattering. Yeah, somebody's asking some questions.
yes, sir. Sir, when the temperatures are high, so the electrons have more energy. So, sir, those electrons won't interact with each other, so they might reduce the mobility.
Yeah, so basically, see, you could imagine like a express highway with a lot of cars moving very high speed at the same velocity, right? So they don't interact with each other, right? But if one car brakes, means other car will collide. But
But
that will
they
not
have
happen,
charge.
right? So basically, uh, see, if all the electrons, right, means the electron holes are moving, but they are moving with same velocity, right? Because we are talking about, when we are talking about drift velocity, we are talking about average velocity of the electrons and holes, right? And if they are moving with the same velocity, they don't interact with each other much, right?
Yes, sir.
but they will interact, because when you talk about the crystal itself, right? So there is phonon, there are ionized donors. So this is something like when I talk about cars, right? Electrons are cars, they're moving with some velocity, but the road condition depends on this ionized impurity and phonon, right? So so basically their velocity will depend on the condition of the road, right? So if the condition of the road is very bumpy, right, then their velocity will automatically come down, right, and the mobility will be less. Okay. Uh, so see your drift current that we had discussed, right? So this is charge into velocity, right? And your velocity, this is the drift velocity. This is nothing but mobility times electric field. So electric field is how much potential difference. Let's say you are taking a semiconductor. So electric field is nothing but how much potential difference you are giving across the semiconductor. That will determine your electric field, right? So if you are V here, and so this is nothing but, in this case, if this is L, so electric field will be V by L, right? Right. But your mobility is your condition of the semiconductor, right? How highly it is doped, and what is the temperature, ambient temperature, and all those things, right? So and the charge here, charge is how highly it is doped, right? If it is doped heavily, that means we have a lot of electrons, right? So your current will depend on charge, that depends on the doping, right? This is nothing but Q times N, right? If you have more number of electrons, you'll have more current, right? And N is nothing but your dopants, right? Number of dopants, right? So if it is 10 to the 19 per centimeter cube, that means you have N equal to 10 to the 19, right? So higher the charge, higher will be the current, right? And also at the same time, velocity, right? So velocity has two terms, mobility and electric field. Electric field is the whatever voltage difference you are applying, because here the electron holes are moving because of the applied voltage difference, right? By drift, right? Electric field. And if your applied voltage difference is less, that means if your electric field is zero, your current will be zero, right? Right. So and mobility, right? And mobility is a function of dopant, is a function of ambient temperature and everything, right? So uh, so you couldn't really say, if I go on increasing your dopants, your current will be very high, because your mobility may degrade very fast, right? Because with very high doping condition or a very high temperature operation, right? So uh, so here the two things are very important. Mobility, first, mobility is a very important factor, right? And then the charge, right? And the electric. So basically your current will depend on charge, mobility, and electric field, right? And your mobility is very complex, right? So it's not very straightforward that the mobility, because mobility will depend on the scattering. Here we have only talked about two scattering phenomena, right? We have many scattering phenomena in a semiconductor, right? So means these two are very important, ionized donor scattering and phonon scattering, but we have other thing, right? And now you see, as you go on increasing temperature, you go to very high temperature. That means electrons are moving with very high velocity, right? So they are not affected by the ionized donors, right? But when they're moving at very high velocity, and we are talking about high temperature, right? So we have phonons, right? So we have very high energy phonons, right? So they interact with very high energy phonons, right? These high energy phonons are optical phonons, right? And optical phonons uh, are very powerful, right? So basically, when they interact, so electron is a wave, right? And we have phonons is also wave. When they interact, so basically they'll not means they'll not allow the electrons to move with very high speed, right? That's the reason you have velocity saturation, right? And the velocity saturation phenomena is because of optical phonon scattering, right? And optical phonon scattering happens at different, because optical phonon scattering will depend on the band structure, right? And band structure will depend on the lattice constant, right? So that's the reason your saturation velocity is different for different semiconductor. For silicon, we have a saturation velocity which is 10 to the 7 centimeter per second. If you for gallium arsenide, you have a different saturation velocity. If you go to gallium nitride, you have a different saturation velocity. So saturation velocity is also different from semiconductor to semiconductor, right? Okay. All right. Any questions here? Shruti?
No, sir, it's clear.
Okay. Nishant?
No, sir.
Swati? Om?
Sir.
Monica?
No, sir.
So it is clear.
Right. Good. So, okay. Yeah. So there is no question. So maybe we should I'll